A hovercraft is a simple vehicle working on the process that there is a cushion of air beneath the actual hull of the vehicle which keeps it off the ground. This is such that there is low friction between the hovercraft itself and the ground. In fact, the friction is between the hovercraft and the air, such that a small pushing force will produce a great distance moved by the hovercraft. Our hovercraft, in essence, involves a piece of plywood with a hole in the center, a leaf blower as our engine to push air through into a skirt beneath it. The skirt that we made is made out of tarpaulin. In our skirt, we also have small holes at the bottom which allow air to flow through, which prevents any bursting of the tarpaulin. However, the basic principle is the same, because in that skirt that we built under our plywood, there's a high pressure maintained there such that there's distance off the ground from the skirt, and the hovercraft itself is able to travel.
I'd like to discuss the mathematical model for our hovercraft system. First of all, we have to discuss how we get the total mass of our hovercraft, plus its payload plus the pilot. So we denote total mass as m subscript t, which is the mass of the pilot, the mass of the payload, and the mass of the hovercraft, which works out to be 120 kilograms. Now, the pushing force F subscript t is 220 newtons, which we discovered from an online article which gathers the average pushing force of a human being. Now, the frictional force is the product of mg and mu k, coefficient of friction, which was found out to be 47.09 newtons. So, from this information, we can plug it into our mathematical model, which we model as mx double dot, x being the displacement of the hovercraft moved, and x double dot is the second differential, which is also equal to the acceleration, is equal to Ft, the pushing force, minus the frictional force, Fk. So, plugging in the values for m, Ft, and Fk, we get 120 x double dot is equal to 120 minus 47. So 120 x double dot is equal to 173. Now, moving on, to find the transfer function from this, we find the Laplace on each side. So we find the Laplace of 120 x double dot and the Laplace of 173. So bringing the 120 on the outside since it's a constant, we get 120 into s squared xs minus sx0 minus x prime 0 is equal to 173 on s, because the Laplace of a constant is 1 on s. Now, when working the Laplace for our system dynamics model, we must take all initial values to be 0. So from that, we can see that sx0 and x prime 0 goes to 0. So we have 120 s squared xs is equal to 173 on s. So the objective of this is to make xs the subject of the formula. So we will get 173 over s squared by 120. Now, taking the inverse of this, of xs and this function here, you can see we can find xt now, because the Laplace inverse of xs is xt, which gives us a function in time. So we can relate this function in time to our force as well as to our displacement. As you can see here, air pressure must build up in the skirt and then expel through small holes at the bottom of the skirt, creating a small cushion of air, causing lift, reducing the friction needed and thereby the force needed to push the hovercraft. Now, the main problem with this first design where the hole in the center was that we wouldn't get an even distribution of air throughout the hovercraft, which created some areas of the hovercraft, mainly where the pilot was sitting down, to sag more, and the areas where there was less weight to inflate more, creating like a seesaw effect, where one side was higher than the other due to a difference in air pressure. To try to alleviate this, we initially tried to create more holes in the side where there was more air pressure, well, more air volume, which was the side where the pilot was not, the opposite side to the pilot. But this didn't work so well. There was still too much friction between the skirt of the hovercraft and the ground, and too much force was required to push the hovercraft.
At this point, we decided to build a prototype before rebuilding our current design in order to know the way forward and to make sure our design was working. Therefore, you can see our prototype beneath. This time, in order to solve the problem explained before by the skirt, we actually secured the center of our tackle, or of our skirt, to the plyboard, such that there is no air that needs to be going through this main section to provide lift. Because of this, it creates a smaller area itself that needs to be inflated in the first place, and this will make it easier on the blower we have. As well as we readjusted the position of the holes in it to channel airflow so that we could keep pressure uniform throughout this new skirt design. And hopefully it will work, and as we tested, as we shall see, it did. As you could see, our prototype is easily inflated with the skirt and is even this time. As well as it is way easier to actually push the hovercraft and get movement on it. Therefore, we decided that this prototype was suitable to proceed with and to build our final design based on this.